Hi, my name is Delaney Farrell. I'm a PhD student in the computational science program. And at San Diego State, I study under Dr. Friedhelin Weber. And today I'll be talking about a project we've been working on that explores the structure and stability of differentially rotating compact objects, specifically neutron stars. So around 5% of observed neutron stars exist in stellar binary systems, and these can be between neutron stars and other compact objects like white dwarfs or black holes, or between two neutron stars. When a binary neutron star system, like the one I've shown in this right side diagram, inspiral and eventually collide, the collision will produce a compact remnant star that can effectively take one of three forms: a supermassive neutron star, a hypermassive neutron star, or promptly collapse into a black hole. So I'm going to focus in on one of these three potential outcomes, specifically the hypermassive neutron star remnant. And these stars have several interesting properties that a quote-unquote regular neutron star wouldn't have. So as the name suggests, these stars have incredibly high masses, or masses great enough to collapse into a black hole. These stars are only stable on short dynamical timescales on the order of milliseconds to seconds, and their short-term stability may be attributed to a unique type of rotation called differential rotation. So most isolated rotating neutron stars are believed to be rotating uniformly, or as a rigid body, where the rotational frequency within the star is a constant. But following extreme astrophysical events like a binary neutron star merger, a compact remnant star might be rotating differentially, where the internal regions in the star will all rotate at different frequencies, meaning the rotational frequency is no longer constant within the star, but it's dependent on the radial axis, like this schematic diagram I've shown here. So this unusual rotation is the mechanism that allows these stars to sustain incredibly high masses. So in order to model these hypermassive remnant stars, we devised a numerical scheme to model differential rotation in neutron stars. So I'll very briefly touch on the numerical simulation. It's a code I named DRNS for differentially rotating neutron stars. The simulation begins with the user supplying what we call an equation of state model, which describes the pressure density relationship within the star. The calculation boils down to solving the metric functions using Einstein's field equation. It's a lot of complex physics, but it reduces to a system of 5 nonlinear partial differential equations that are solved in an iterative scheme on a 2D grid, radial axis by polar axis within the star. So in general, numerically simulating rotating neutron stars, either uniformly or differentially rotating, is a much harder task than modeling non-rotating stars. And there's a few different reasons that I've listed here. The first is that the metric functions in rotation or rotating neutron stars depend on both the radial axis and the polar angle, while non-rotating stars have only a dependence on the radial axis. And the reason that the polar angle comes into play for rotation is that rapid rotation can actually deform the structure of the star, deviating from spherical symmetry. And we'll touch on that a little bit more in a moment. Additionally, rotation induces frame dragging in the space-time around the star, which is shown in this photo on the right with a little omega. Lastly, rotation creates or allows for heavier stars, and this additional mass can change the space-time geometries within the calculations. So not an easy task. And then I'll briefly touch or show some results highlighting both the expected increase in mass and structural deformation from rapid differential rotation. So in this first plot here on the left, I've shown mass density curves for 4 different degrees of differential rotation that are all characterized by this parameter A inverse. It's a scaling parameter used to increase or decrease the level of differential rotation. This parameter can hold values from 0 to 1, 1 being the most extreme level of differential rotation. And the general trend that we see is an increase in mass as we get more and more extreme in our degree of differential rotation. And this is compared to a non-rotating mass curve, which is shown with the black dashed line. And in this second set of plots here, I've shown energy density cross sections or side views of a star with the same 4 degrees of differential rotation. So for rapid uniform rotation, we expect to see a lengthening along the radial axis and a shortening from top to bottom. We see the same trend here, but for the highest degree of differential rotation, A inverse equals 1, shown in this bottom right plot. There's a slight pinching forming at the top and bottom of the star. We call this a quasi-toroidal shape, which is starting to form. This is an extremely unstable configuration for these stars, but really interesting in the context of differential rotation. So I'll go much more into detail on these results at the ACSESS event on April 7th, and I hope to see you all there. Thank you.